Nati, and in this video I will tell you about our work on using deep learning for data analysis of envy center-based nano-NMR. So in nano-NMR we would like to estimate or discriminate between spectrums, frequencies of tiny amounts of molecules. And in such setups there is this strong noise that we want to filter out from the data that we measure. And if we have a full knowledge on the noise model and the physical model, then we can use Bayesian methods that will give us the optimum information that we could get. But usually we do not have that information and we have a problem. And what we want to show in this work that it could be possible to use neural networks to apply on the measured data that will learn by themselves the noise model and will give us the optimum information. And we consider in this work two problems, frequency discrimination and frequency resolution. So in frequency discrimination, we have a signal that could be of either one of two frequencies, omega 1, omega 1, that we measure. In the figure, we see measurement results obtained by a single envy on artificial signals of two frequencies. On the left, we see the Fourier transform of the measurements, and we can see that we cannot discriminate between the two frequencies based on the Fourier transform alone. On the right, we see the measurement result, the trace of the measurement result, the bits 0s and 1. And we can see that we have mostly zeros. This is because of low efficiency detection. And this is an experiment when the SNR is very low. So in general, we consider discrimination methods that we input to the method the string of bits, and we want to get an estimation of either these measurement results came from a signal with the frequency of omega 1 or a signal with the frequency of omega 2. And the way we want to use it with deep learning is to input the string of bits, the measurement result, as the input to the neural network, where at the end the neural network will output a discrimination result. So it would be either the label would correspond to either the first frequency or the second frequency. So we first consider a numerical analysis of the ideal model where there is no noise. There is only a random phase, which is given here by phi I, that we don't know it. It is uniformly distributed random phase. And in this case, we can calculate the Fisher information. So we have a bound on the maximal information that we can get. And in the figure, we see the error probability of the discrimination method as function of the as function of the difference between the two frequencies. So we consider three methods. The first in green squares is the full Bayesian methods when we do the maximal likelihood ratio test with respect to the random phase. The red circle is the deep learning method, and in blue we have a correlation-based method when we estimate the frequency based on a two-point correlation, which is kind of a more fair comparison to machine learning because we assume no a priori knowledge on the physical model or the noise model. And in this case, in this ideal model, we see that all methods reach the optimum. Okay, then we introduce the inefficiency in a way that corresponds to the inefficiencies of the experimental setup. And we see here again the error probability as function of the frequency difference between the two frequencies of the signals. So the numerical data is represented by the green squares for the full Bayesian method, again with respect to the unknown phase. And in red circle, we see the performance of the deep learning neural network, and we see that they are both doing the same. But then we applied it to the experimental data, which are the diamonds, the blue diamond and the green diamond. So the blue diamond corresponds to the deep learning, and the green diamond corresponds to the full Bayesian method, the maximum likelihood. And here we see the difference. We see that the deep learning neural network performs better than the maximum likelihood test because in this case, we don't know, there is noise that we don't know exactly the noise model, and the deep learning handles it by, in a way, effectively learning the noise model, while in the full Bayesian method, we have a problem because we don't know the noise model, and the probability function that we use do not correspond fully to the true physical situation in the experiment. And we expect that this gap, the difference between the neural network and the full Bayesian methods, will be larger in true NMR setup where the noise is stronger and more complicated than we had here. We also considered the problem of frequency resolution, where we have a signal of one frequency or a signal of two frequencies. So here the frequencies are given by delta I. And we consider a case when there is a strong phase and amplitude noise, which we model by an Ornstein-Uhlenbeck process. And in this case, these factors of AI and BI undergo an Ornstein-Uhlenbeck process. And again, we compare the error probability of discriminating between the case of one frequency or two frequencies as functions the difference between the central frequency and the two frequencies. This is delta omega. And here we see that the deep learning method performs slightly better than the full Bayesian method that we use with respect to the Ornstein-Uhlenbeck processes themselves, and also it performs better than the correlation-based method. And also in this case, there was a big difference in terms of computational resources and runtimes of the discrimination methods. So to summarize, in this work, we wanted to show preliminary results that deep learning methods could be useful for nano-NMR setup, for data processing of nano-NMR setup by the fact that the deep learning neural networks could learn the noise model efficiently. And we demonstrated it on experimental data obtained by a single NV in the discrimination between two artificial signals. And we showed that the deep learning neural networks can perform much better than Bayesian methods. And in the future, it would be interesting to test this model on true nano-NMR data obtained by a single NV sensor. Thank you.